As always, our recordings of our virtual meetups will be available on YouTube about a week after the meetup, and we will post a message on Meetup when the recording is ready. Next, I am very pleased to introduce our speaker today, Bing Liu. Bing Liu is a distinguished professor at the University of Illinois at Chicago. He received his PhD in AI from the University of Edinburgh. His current research interests include lifelong or continual learning, lifelong learning dialogue systems, open world learning, and machine learning. His previous interests also include sentiment analysis, fake review detection, web mining, and data mining. He has published extensively in prestigious conferences and journals and authored 4 books, 1 about lifelong continual machine learning, 2 about sentiment analysis, and 1 about web mining. 3 of his papers have received the Test of Time Awards, and another one received Test of Time Honorable Mention. Some of his works have been widely reported in popular and technology press internationally. He served as the chair of ACM SIGKDD from 2013 to 2017 as program chair of many leading data mining conferences. He is the winner of 2018 ACM SIGKDD Innovation Award and is a fellow of AAAI, ACM, and IEEE. Take it away, Professor Liu.
Okay, let me share my slide. Can you see it?
Yes, we can see your slides.
Okay. Thanks for the introduction and thanks for the invitation. So today I'm going to talk about mostly about continual learning and also a little bit about this autonomy. How can we make the system autonomous and in terms of learning, in terms of reaction as well. And we have a book about lifelong learning, but it's a little out of date because in the past few years and the movement has been quite fast, but the basic idea are still there. So in the traditional machine learning, and we talk about this sort of isolate a single task. You're learning one task. You have a task of a piece of data, and then you have a machine learning algorithm, which we call the learner, and that produces a model. And the model I'll be using application. You've got a sensor, and then you model make some decision. You execute some things in your application. Somebody has a question. Okay. So you can ask me questions anytime that you have one. So the key weaknesses of this particular paradigm of classical machine learning is the first one is the closed world assumption, which basically means what you see in testing will be exactly the same thing as you see in training. So you are not saying anything new or novel happening in application, which is normally not true because in practice, when you go to do sort of your performance task, you always see something unexpected. And then how do you deal with that? How do you learn about that? Which will be part of the talk today. And also the previous learning algorithms or paradigm does not really do continuous kind of learning. So you basically focus on one task, you collect lots of data, and then you learn from that data, and you build a model, and then the model goes to application, and then that's it. But we're going to talk about the learning after deployment. So the post-deployment phase, and the system basically going to see the real cases. And in this process of receiving real cases, if you see something unexpected, something novel, and then can you recognize it? And then can you learn about it? And how do you do it? And how do you do it? We're going to talk about that as well. So the first thing I will give you a short introduction of lifelong learning or continual learning. So basically, in the early days, people normally call it lifelong learning, but nowadays mostly in the machine learning community, people call it continual learning. But in the industry or this industry, and also when people talk about it, people like to talk about the lifelong learning, because lifelong learning sounds a little bit more easier to say or whatever, easy to understand. But these two terms basically means the same thing. Lifelong learning or continual learning, it basically means the same thing. So what it means, it learns a sequence of tasks incrementally. So it's basically try to simulate what human being is doing in terms of learning. I learned something today, I learned something tomorrow, and then after that, and then this basically is a sequential process. And it is also an incremental process. Okay, it's not sort of saying you put all the tasks together and you learn them together, and which doesn't really happen in real life. It doesn't really happen often in real life unless you are doing sort of learning by instruction. So some teacher teach you something and you learn from that. You can learn a lot of things together. Okay, together. So the goal of this lifelong learning essentially is to try to learn this incrementally and without catastrophic forgetting, which basically means when you learn a new thing, are you going to forget what you have learned in the past, or are you going to interfere with what you have learned in the past? This is a very important problem. It's a very, very challenging problem, especially for neural nets. So we're talking about the neural nets. One neural net, we're going to learn all the tasks. So sequentially learning individual tasks. And then if you do this incrementally, which basically means when you learn this new task, you don't really have the training data for the past task. Maybe you have a little bit, but not a lot. And then when you learn this new thing, you're going to change the neural nets, right? You're going to change the weights and the parameters, and then to suit this new task. But those weights and those sort of parameters, they were learned already for the previous task. So when you learn a new task, if you cause some change to those parameters, and then you are going to sort of cause some forgetting, which basically means the degradation of the accuracy or whatever measure you use of the previous task. So you may not be able to do the previous task well. So this is one of the major challenges, and it's still very tough to solve this problem. Another sort of objective is the knowledge transfer. When you have when you learn a new task, you obviously want to use the previous task knowledge you learned in the past to help you learn this new task better. Okay, learn this two tasks better. Here is the new task, we call it TN+1. So the assumption is once the task is learned, the data of that task will no longer be accessible. So it's just like what we humans do when we see some, let's say we see some chickens or something, and we learn to recognize chicken. But tomorrow when I see some rabbits, I learn the rabbits. I mean, I don't really have the chickens sort of those videos in front of me anymore. And so that's making it problem difficult because you cannot learn everything together because the data you have seen before, they are no longer accessible. And that's also the problem that caused this catastrophic forgetting, and also the problem of the transfer, because what you have learned becomes some network parameters on those things, and then you don't have the data, and then the knowledge transfer becomes tricky because you don't know which part of knowledge can be transferred and which part cannot be transferred. So if you do not do it carefully, you can get negative transfer, which basically means you want to use the past, but the past is going to hurt you. It's going to hurt you. So I hope you get the idea. So we're learning a sequence of tasks and incrementally. That's essentially what the lifelong learning is doing. Okay, so it's doing. And so if you see this pictorially, and then we have this task T1, T up to Tm+1, and this is the new task or the current task. You have the current task data. So all the previous tasks has been learned, and then you go to this continual learner, and then you have the knowledge base. Okay, this knowledge base basically then stores the knowledge you learned in the past. And then when you have this new task, you want to have some knowledge which is suitable for this particular task, and that can be used to learn this task to produce a better model. So that model goes to the application. Okay, so this is the sort of traditional lifelong learning or continual learning paradigm. Okay, paradigm. So there's a few characteristics, and we're talking about the continuous incremental learning process, which is essentially what the way we can do as a human. We do this quite well, but currently computers still cannot do that. And one of those big issues is the way described is the catastrophic forgetting. So you basically you learn the new thing, you forget what you learned in the past. And of course, this of course involves knowledge accumulation, because we learn so many tasks, we want to remember them. Okay, we want to remember them, and then finding the knowledge transfer. Of course, this knowledge transfer can be the forward transfer and can be backward transfer. Forward transfer basically means what you have learned in the past can help me to learn the future task better. And the backward transfer basically means when I learn a future task, I can improve the model for some previous tasks because they might have lots of similarities and they have some shared knowledge among them. So you can do that. So that we can do backward and forward. But in most cases, it's pretty challenging, especially the backward transfer, because if you want to do back transfer, you are going to change the previous model, and the previous data is no longer there, and then this can get very, very tricky. Very tricky. So if you don't do carefully, you can hurt the previous model. So there are several settings. There's actually many settings for this continual learning, and so at least the first thing we need to understand is that they're all learned in a single neural net. So what is the idea here? The idea is basically saying human beings have only one brain. We assume that's a big neural nets, okay, big neural nets. So everything are learned in this single brain. You are not like in the past we build sort of individual models. So for example, when I do this SVM and these are all individual models. So the models are completely isolated. They're nothing to do with each other. Of course, they can't help each other unless you want to sort of borrow physically, say I'm going to use something from that previous model. But in this neural nets kind of sort of scenarios, we want to have this knowledge transfer, everything done sort of automatically. So there's two kind of setting which is most popular. One is called class incremental learning or class continual learning. That is essentially to produce a single model for all the tasks. So what do we mean by a task? A task basically means there's a few things I want to learn. For example, today I want to learn, I probably got some training example of a chicken and rabbits. Okay, today I got this two classes or two category of things, and I want to learn how to recognize these two guys. And so this can be regarded as one task. So tomorrow I may be seeing, I may see a dog, for example. So, and then I'm going to learn the dog. So that dog is also a task. But of course, in the day, you can see a dog and see a goose, for example. You can learn them together. So that's a task. So you can see that we have a first task is the chicken and the rabbits, and the second task will be the dog and the goose, for example. And then, so we have two tasks. Okay. So the class continual learning just basically says, although we have two tasks, but I only have one model. So what does that mean? It basically means when we come to the test time, I give you an animal, and can you tell me which one of these four animal it is? Okay, so we don't really have the task information anymore. It's not say when we learn it, we have two tasks, but when we test it, there's no task anymore. We just basically try to recognize those four type of animals. Okay, so that's the most challenging situation. And then this is also, of course, what human can do very well. And we can learn to recognize something tomorrow. We can learn something else, and after that, we can learn a lot of stuff. And there was not much interference. What we have learned in the past, that's still there. Okay, and then as time goes by, you still can recognize those things you learned in the past. But this is a major problem for lifelong learning or continual learning, because you can cause quite a bit of forgetting, which basically means what you have learned in the past, and that classification becomes sort of become worse, quite a bit worse. Okay. The second one, which is popular, is called task continual learning. So this one is more like you learn each task separately. Basically, although we're still doing in a single neural nets, but they're somewhat separate. Basically means that each task they have nothing to do with each other. So when it comes to test time, I have to tell you which task I want to test. So now you basically have the task information. So previous one, we don't have the task information. For example, today I want to do some classification of text documents. Okay, let's say I have a politics and sports and the computer. This thing that I want to learn. I want to recognize, basically I want to classify this kind of text. But tomorrow I learned to recognize animals. Okay, or maybe the day afterwards I classify the sentiment. For example, I give me a document. Is this a positive review or is a is a negative review. So you can see this task can be quite different, but they are learned in the same network. And then in this case, you have to give me the task, because I give you a document. You can classify this as a politics document, as a sports document, but you can also classify in terms of sentiment. Okay, in terms of sentiment. So it depends on what you want, and I can use the model to perform the task you give in terms of at time of testing. So you can see that there's a difference. So the first one is just that at the test time you don't have any information of the task. But in the second situation of the task, incremental task, continual learning, in the training time we have the task, and the test time we also have the task information. So the second one is actually much easier. And actually, the second one is pretty much solved. You don't really have much of forgetting. In terms of catastrophic forgetting, it's pretty much solved. The only issue in this case is knowledge transfer, because some of the tasks you learned in the past can be related to what you learn in the future. So in that case, and how do we figure out which task will be similar to that future task, and then to transfer knowledge over, and that is still a challenging problem, and because it's not easy to identify which one is similar, which one is not similar. Okay. So now the problem, of course, is the class incremental learning, which is very commonly done as humans, but it's very tough for computer. Okay. And also is one of the biggest challenge for practical application of continual learning, because most of the continual learning application, real life application, is more like a class incremental learning. Okay, for example, you have a self-driving car. You go to drive on the road. You probably learn to recognize pedestrians. You learn to recognize the cars and trucks, all these things. But now I see something. For example, I see a piece of leaf flying in the air. So now that is sort of another thing you need to learn incrementally. For example, you've never learned that thing before, but now you have to learn that. So you learn that next time when you go to drive, you see a piece of leaf, you should be able to recognize a piece of leaf. You will still be able to recognize your original pedestrians, all those cars and trucks, all those things. They're all together. But that's a lot of application like that. Even in the chatbot kind of situation, when we build a chatbot, we basically say this chatbot has lots of skills. For example, this one can tell me the weather information. Another one can book in tables in the restaurant, and another one can probably help me to reserve hotels. But and then next time I want to learn some new things. For example, I want to learn how to sort of book a flight, okay, and how to sort of buy a train ticket, for example. So those things are those are new things, incrementally learned. But when you come to the common application, I mean, the user is not gonna tell you, oh, I'm gonna use that particular task. I'm gonna use this particular task of booking train tickets, okay, to buy train tickets. But I will just say, no, okay, buy me a train ticket, and then you have to figure out what my intention is. So that's essentially a class continual learning problem. Okay, I'm not going to tell you, now I'm going to do this particular thing, and then you only focus on this thing. Don't worry about other thing. I mean, I'm just telling you something, and you just do it for me. So my intent has to be classified. So that becomes the class continual learning problem, and that's very challenging. So there are many approaches, and the regularization-based approach, and that's a machine learning. So you want to regularize, basically you try to penalize changes to the parameters. So what happens is that we have really learned many tasks, and then those parameters has been sort of fixed for those guys in the past. So when I adding a new task, I want to sort of try to keep the previous parameters, at least those parameters important to the previous task. Okay, so what the regularization is doing is essentially when you have a loss function and you add some regularization, is a penalty term, which basically try to say, if you change the previous stuff, and I will penalize you. So you try not to change the previous parameters, and then when you learn the new one. So of course, what you can do is basically you find out those parameters which are important for previous tasks, and try not to modify those guys too much. And so those parameters and those neurons which are not so important for the previous task, then you try to modify those guys. Okay, so try to modify those guys because they are not important to the previous task. So in this case, we're trying to try not to damage the previous, not to interfere with the previous task parameters too much. So the second one is experience replay. So this basically means I'm going to save a little bit of data, not much of previous tasks. Okay, because when I learn this new task, I don't have if I don't have anything from previous tasks, this is very challenging. And but if I do have a little bit of data from the previous task, I randomly sample some previous training data, and now I'm going to learn this new task, and now I can jointly learn all this together. So this is small amount of data from the previous task can help me to adjust the previous sort of those parameters to make sure those parameters, the parameters which has been changed for me to learn the new task and also suitable for the previous task. And again, this is also not good enough because if you save not a lot, and you may not be able to just enough to not forget anything. Okay. There are lots of sort of algorithms. And otherwise, the generative replay, I generate the past data, because I don't really have the previous data, but I assume I have a generator. For example, the human can do this quite well. For example, I see a dog. Tomorrow, when I see a chicken, for example, I see a wolf, and then which is somebody tell me that's not a dog, and it's called a wolf, and then you can sort of imagine, you can say, oh, the dog is on this part is different from the dog, from this wolf, because you can generate something. And although you may not be remember exactly the dogs you've seen before, but you do have an image of the dog, right? That sort of you can generate in your brain somehow. And also, some people even can draw it, right? And they can draw it. Basically, they build some kind of generator in the brain. So this is essentially trying to use that kind of approach way. And when I learn to recognize that particular animal, at the same time, I learned how to generate that animal images. Okay, animal image. So when I learn a new task, I can use those generated things to help me to learn this new thing, and also to adjust the previous task to make everything works well. Okay, of course, generation is not perfect. So you generate something different, and again, which is cause some problem because if the generation is not perfectly suit sort of the previous thing, and then you cause some sort of forgetting as well. Otherwise, called the parameter isolation. This four are fairly popular, and parameter isolation is mostly for this particular thing, for task continual learning. And essentially, it says I'm going to isolate. I learn this particular task, I will protect it. For example, I can use masks. So, for example, this bunch of neurons are very important for this particular task. I have masked this guy. I said this guy's already been taken. Somebody have used this one already. So if you want to learn a new task, don't touch those guys. Okay, you can use those guys, which basically in the forward pass, when you do the neural nets, when you do the forward pass, you can still use those guys. But when you do the backward pass, when you do the back propagation, you cannot change those weights. Okay, when you compute the gradients and then you want to do the SGD, and then you basically should not change. Okay, you should not change those guys. So this becomes isolated. So in this case, and then you can pretty much fully protect the previous task you learned. And in this case, if I do know the task information, and then I can say, oh, okay, I'm going to use this particular task now. So for example, I'm now going to do the sentiment classification. So I'm just using this sort of subnetwork, essentially the subnetwork, and then which is not going to cause any forgetting. So I can do as I first I did it. Okay, when I first did it, now and later I want to do it, and then still pretty much the same. So this is the one. This is basically the main approach which solves this particular problem, task continual learning. But of course, this is not suitable for the first one. Okay, for the first one, because even you protect it, and that's no use because at the test time I'm not going to tell you which model you should use. So you still have to choose which model, and that's still a problem. Kind of still quite a bigger problem. How do you choose? Okay, how do you choose is pretty complicated. Okay. And this also have two kind of a mode. The one is batch continual learning, another one is online continual learning. So batch continual basically means I have all the data when I start to learn this particular task. So for example, I already manually labeled a lot of data when I have this new task. For example, I'm learning the rabbits, and I got lots of rabbit images. Okay, I can learn this particular task, and I can learn to recognize this thing quite well in one go. So in the training, I can use a lot of epochs. Okay, I can do a lot of epochs to perform my training to have the loss down. But online thing in the situation is more like continually streaming. Data comes in streaming. So the data basically comes gradually, and when you see a little bit of data, a small batch of data, and then you have to train your model. You have to update your model. So as time goes by, you basically update your model many times. And since the data comes in the streaming, and you only can see the data once, and then every time you basically you train with that small amount of data, essentially like you are training the data in one epoch. Okay, so that is of course is much more challenging, and you can't achieve very good results because you only train one epoch effectively. But in most of the in sort of batch continuum, you can train a lot of epochs, and then obviously you can learn a more effective model. Okay. But in real life, many cases are like sort of like a continual learning, because for example, when you see something, you see some dog today and you learn that, and tomorrow you see some different dogs, and you say, oh, that is also dog, then you learn that. So that just becomes sort of online kind of situation, because you don't really learn all the dogs together. Today you see some dog, you learn that. Tomorrow you see dog, you sort of improve your model. Today you maybe see some black dogs. Tomorrow you see some white dogs, and the day afterwards you see some small dogs. So you can, and then because the data comes sort of gradually, you don't see all the data together, and so that makes the problems even more challenging. So most of our applications still not be able to, the application still pretty much lagging because lots of technical problems not solved. Technical is probably not solved. So I just give you some example of this pre-deployment continual learning. Okay, post-deployment, it just basically means after the model has been deployed, can I still learn? Because most of the situation when we talk about machine learning, we are always talking about pre-deployment, because we basically build a model. The model is already working very well, and then we're going to send for deployment and to do its intended performance task. Okay, so let's talk about this batch continual learning. Okay, I just give you an example, and it was published last year. So this is trying to deal with catastrophic forgetting, and we learn one thing at a time. And for example, I now learn to recognize chicken. Next, I recognize dog, and then after that, I learn to recognize a sheep, and those things. Okay, you one class at a time. And so this is essentially the sort of a problem of continual per task continual learning. Okay, this is even more challenging because in traditional sort of supervised learning, you have more than one task. You have more than one class you can compare with each other, right? But when you only have one class, this becomes very challenging. Okay, how do you learn this particular class? Because you have nothing to compare with. Okay, nothing to compare with. So in this case, we essentially propose kind of mostly the contribution here is mainly about this holistic regularization. The first part of it is essentially is the negative likelihood, okay, negative log likelihood stuff. And that is not so much, but there is the second part, which is what we call the holistic regularization. What does that mean? Just basically means we don't want to have this model which choose only biased features to recognize this particular class. We want this sort of features to be spread. okay, to be spread. So equally important. So you have lots of features, and the other features are sort of not necessarily equally, but they're similar to each other. They're not some features very important, and some features are less important. So that's why we penalize the gradients. Okay, penalize gradient if the gradient is too large, because I raise the power to many, and then we want to bring it down. Okay, we want to bring it down, so make everything so evenly used, sort of all the features are evenly used. So in this case, essentially, when we have a feature extractor, and then we can use each of this to learn individual model to recognize each individual class, and then this we can learn sort of individually, and this does not have any forgetting. However, if you learn individually, you don't see other guys, and when you come to the classification, that becomes the problem, because you can only say this is not me, or this probably is me. So you have to compare this thing. You compare the sort of magnitude of your output response, and which is also cause some challenge. Then there are some details we try to deal with that, and I'm not going to talk about that. So of course, the result is pretty. It's much better than without using this particular organization. And this is another one, which is talking about the previous. This one is a class incremental learning. So I'll give you another example, which is it's also a batch continual learning, but it's a task incremental learning. So in this case, we say we learn individual tasks, and the test time we also knows which task model we want to use. Okay, for the previous one we don't know, but now we know. So in this case, much easier. And so in this case, we're dealing with both problem of forgetting avoidance. So we don't want to cause catastrophic forgetting. And we also want to know the knowledge transfer. Essentially, in this case, we learn a lot of tasks. And so when we learn a new task, we want to know which previous task model can help me to learn better. Because it could be lots of reasons. It could be the amount of data is not sufficient, or you can some corner cases you did not cover, but it was sort of similar to something you've learned in the past. So this is essentially we want to deal with both problems. And so the technique to deal with the first problem of forgetting is based on some masks. So it's basically we identify a subnetwork. Okay, to identify a subnetwork for each particular task. Okay, and as I said, this is essentially approach uses a parameter isolation. Okay, parameter isolation approach, and we identify subtask for this particular problem, and then for a particular subnetwork for this particular task. And the forward, you have no problem, you can use it, but the backward, you cannot change it. Okay, you cannot change it since you are being blocked for the previous task. So in this case, the challenging is the knowledge transfer. So how do I know some previous task is similar to my current task? I can use that to help me to learn better for the current task. So in this case, we're talking about the forward knowledge transfer and the backward knowledge transfer. So one way to detect this is we build a reference model. So essentially say if I don't use any of the previous knowledge, and what can I achieve? But if I do use some previous knowledge, what can I achieve? So essentially, when I try to compare these two things, if one guy is doing better than if I use something in the past that can help me to do better, I think that is sort of similar to my new task, which probably can give me some knowledge transfer. And so in this case, when I learn this new task, if I know that and learn this new task, I can open those those masks. So I can when I learn this new thing, I can open the mask of those old tasks which are similar to me. Okay, and then I can update those guys and at the same time learning myself. So in this case, of course, when I learn myself, I can do some forward transfer. If I can modify the past a little bit, which basically achieves backward transfer of knowledge. Okay, transfer. Essentially, that's the idea. So after we detect, if we see this architecture, we know the task ID. So we essentially, this is a task-oriented, okay, task-oriented or task incremental learning. And then we know the classification heads on the things, and then we detect those similar tasks similar to us, use this particular thing to do it, and then we find those things similar, then we essentially use some kind of ensemble thing, so the attention things to put things together to help us to do better with this new task. Okay. And so this is just some result. It shows it does better. Okay, that's better. I'm not going to talk about this not much. Okay. And so I also want to give you an example for online continual learning. So the batch continual learning says when I have the task, I have all the data ready. So continual learning is when I have the task, but my data comes slowly. It comes slowly, and I have to basically get a small batch of data and start to train. Okay, keep training the model. Okay, so in online, and this is the thing we are going to publish soon. It's called online continual learning based on mutual information. So the objective is again to deal with catastrophic forgetting. CF is catastrophic forgetting, and CL is sort of class incremental learning. So the class continual learning. Okay, it's the same thing. So what we want to do in this case is when we learn every task or to learn each iteration, each small batch of data, we want to prevent the information loss in future learning. Okay, and also at the same time we want to preserve the previous learned knowledge. Okay, and so we need a new kind of a learning strategy. I'm not going to talk about a semantic analysis here, but just what is the idea? Okay, the idea. So I give you a problem description first, and now I'll tell you what the idea is. So in this particular case, and we have the training data, and then we have the actually I already said essentially the data comes gradually, and whenever a small batch of data denoted by an X new, and there was a small number of samples, normally 10, for example, 10 samples, and then from a particular task T, and then it's accumulated, and then we'll start to train in one iteration. Okay, and then the data is basically thrown away, gets thrown away. And then we see the next one, and then we train the next batch, keep going until we finish this particular task, the data of this particular task. So this in this online continual learning, very interestingly, the online continual learning, almost every algorithm uses replay. What do you mean by replay? As I said just now, essentially for the previous task, I save some data. Okay, I'm not saying I'm going to destroy. I'm going to discuss all the data from the previous task. I still save a little bit. I save a little bit data from the previous task. Okay, I have a memory buffer. Save those things, and then when I get this mini batch, and to do the training, the mini batch consists of this new X new is basically this is the new data. X buff is from the buffer. So this is a sample from the buffer, which I saved for the for those data I've seen in the past. Okay, sample that, and this memory is called. We use the call this memory, and then we join to train this thing together. Okay, train together. So of course, in the normal sort of neural nets, we have the feature extractor, and we have the classifier. We have the classifier, and then we use this to formulate the loss function, all these things. So the problem, why do we do this mutual information? And the main issue is this problem of cross entropy. Actually, it's not just cross entropy, but this is true for any sort of loss function you use for classification. So the popular cross entropy is the popular, probably the most popular sort of loss function for supervised classification. So what this guy does essentially is to identify those discriminative features. Okay, you learn the discriminative features, which is able to separate the classes of each task. Okay, so this is what do we call it? Discriminative feature is just basically is based on this bunch of features, I can separate the classes I'm learning. And we say this is biased because you might be sort of forgetting about you may sort of neglect many features which is not necessarily important for this particular classification. For example, I see black dogs and white chicken. So I learn this probably color is good enough. I don't really because all my training data and the dogs are all black, and all the training data of all the chickens are white. So then I don't really need to know the shape or whatever of this chicken. Then and the dog, I only need the color. Okay, I don't need the color, which is good enough. But tomorrow I see a white rabbit. Then that feature you learned in the past is no longer valid. It's no longer good enough, right? Because that's white, but it's a rabbit. It's not a chicken. Right? So that is the problem, which is causing the forgetting, because what you learned in the past is not good enough for my new classes or new tasks, new classes. So if that is not good enough, in order to learn a new one, you have to modify the previous sort of parameters in the neural nets, and that causes forgetting. Okay, causes forgetting. So one way to deal with that, to at least to eliminate, to sort of reduce the effect of that, is we try to learn the full features. Okay, full features. So don't neglect anything you think is not important for your task. But that feature, although it's not important for your task, but it can be important for future tasks. Okay, if that is not there when you learn the future task, then the future task is going to modify you. And then that's cause forgetting. Okay, so mutual information is able to help us a little bit on that, help us to some extent on that, of course not completely. Okay, so this is essentially the idea. I just give you a rough idea. It says when I learn the this is the classified part. Okay, the classified, don't worry about this part. And we are talking about the feature. We want the features to be holistic. Basically means we don't want to lose any features. I don't want to lose any features. So the features, the input will be this basically the x new and x buff, right? And then we have the head. This is essentially the loss function comes here for learning the features, So here is the mutual information. We want the new, the original data and the transformed thing. The transformed thing goes through this network, transformed thing. We want those things, that mutual information, we want to maximize the mutual information. So when you talk about the mutual information, you're talking about a dependence of two sort of two random variables, right? Two random variables. So in this case, we want those two guys to be sort of very correlated with each other. They're not going to be, I have this 10 features, but I only learn one feature. So then they are not really, they're sort of not that dependent on each other. But we want this two things to maximize this mutual information. Okay, so to be dependent on each other, very much dependent on each other. And for the new data and also for the buffer data. So in this case, with this mutual information maximization, we will be able to sort of learn more features rather than learn only those things which are probably good enough for discrimination of this particular task. So we want to learn more features. So at the same time, we have this particular line here, and what we want to say, we also want the mutual information to say, we want to preserve those guys, okay, which you learned in the past. We want, so essentially what you have learned in the past and the way you are learning now, we want them to be similar to. Okay, we want them to be similar to. Okay, so then we can, if we can do this, and we'll be able to sort of cause less forgetting. Okay, cause less forgetting, and of course less modification when you learn a new task. And the feature part, you do not have to change a lot of those features, because I've tried my best to learn all the features possible I can. And now if you have a new thing, which is the features probably I've learned in the past, the feature is good enough for you, right? But you just have to change your classifier. That's fine, because the classifier part, you have a different classification head. You're not going to forget anything in that case. So the issue of forgetting is basically in the feature learning. Okay, in the feature learning. And then we have some result which can sort of result in a major improvement in some difficult task. Somehow easy task, of course, you don't improve much. For the more difficult task, you can gain quite a bit of. So this is the last 3 lines are our sort of results, and just different kind of variations of our thing. And you can see it's quite a bit of lots of info. Just one second. I think outside is noisy. Okay, so now I'm going to talk about the post-deployment continual learning. Okay, post-deployment continual basically means now I have learned this model, and I'm going to put this model to application. Okay, and then to put this application, and in the process I'm doing the application, I probably see something I've never seen it before. So how do I learn at that time? So basically, it's on the fly. Okay, on the fly learning. Okay, on the fly learning. So we also call this the open world, because the world is, when we talk about normally classification or supervised learning, we're talking about closed world. So which basically means what you have learned will be what you are going to see. So whatever you are going to see, you must have seen them in training. In testing, must have happened in training. So that's the case. So in this case, we're saying when we see the real world, we'll see something unexpected. You have never learned before. How do we handle that? Okay. So this is very important. And in the past 2 days, I went for a workshop. We're talking quite a bit about this. Okay, well, one, autonomy. Okay, so you can learn by yourself. You don't have to ask some humans, ask the human sort of engineers to collect lots of data, and then you learn. Can you get all this thing by yourself? Can identify the task, and also at the same time get the training data and learn incrementally. Okay, incrementally. So for example, in the self-driving car, right? If you work on this particular problem, you probably know this is extremely difficult. It's extremely difficult because a lot of things you see in the real life, it's going to be unexpected. Okay, when I work on this particular problem for 1 year, so when I was working on this problem, and sort of in the evening, I thought about the algorithm, and then next day when I drive to the school, I said, oh no, this is not going to work in this kind of situation. So every time it's like that. I've never seen this sort of any idea is, oh, this is good. At least for my home, I'm not talking about a very complicated situation. For my home, just complete expressway, a little bit of sort of in the city area, but most of the time, even the expressway, it's really, oh my God, my algorithm is not going to work. Okay, not going to work because something unexpected happens. So this is really tough to cover all the corner cases. Okay, in the real situation. So can you learn on the fly when you see that unexpected situation? Can you learn it at that time? Okay, don't ask the engineers to basically to drive back to the lab and then label some more data or those kind of things. It takes a long time to do. And can we do that? And so this slide just give you a particular real case, okay, my personal experience. As I said, I consult for a company, self-driving car company, for 1 year. And so once we took the car for a field test, essentially on the road. And when we when we are close to a T-junction, the car suddenly stopped and just refused to move. And then we look in front and the back and the left and the right. There's nothing, because of course we did the test on the roads. I mean, although it's a real road, but it's not a busy road. I mean, that's not many cars. So at that particular time, there's nothing. There's nothing, and there's no car. There's no traffic at all. And the lights, everything was good. Then the guy just refused to move. Okay. Then we have to manually take over, and then we drive the car to the lab, and then go to debug what happens, what happened. Then we find out one of the sensors detect a small pebble on the road. Just detect pebble. We look at the road. We didn't really see anything because the pebble is pretty small. Okay, pretty small. We didn't see anything, and then we have to basically have to change the program, and then label some data, and then you're gonna learn this. Next time when you see this pebble, don't stop anymore. Okay. And so, but what happens if at that particular time the car has already detected this thing, right? Can't the car tell me, okay, I detect something unexpected in this particular location, and what should I do? Okay, at least as the humans, or whether it's the passenger or it's the engineers, we just basically say, oh, that's safe, just go ahead. Okay, so then the car just can go ahead at the same time learn this particular type of object is not a problem. Okay, not a problem. So in the future, you don't stop anymore, right? So this becomes a learning on the fly. So in this case, you can see, as a human, I'm doing some supervision, but this supervision is kind of a very natural supervision, and it's also free. I don't really you don't need to pay me to label this data, right? The car does not pay me to label this data. But if you go back to the lab, you have to get somebody to label this data. And because the engineers normally don't do this. I guess normally you get the third world country, the people in the village, to mark this thing, this is a small pebble, you basically label a lot of this and say, oh, don't, that's this guy, you can recognize that, but it's not a problem. So when we do this on the fly, it's free. It's free. But this is not easy to do. Okay? It's not easy to do. Okay. As we said, the incremental learning itself is already a major problem. Okay. This is essentially a class incremental learning. Okay. Because previously when we our perception system learned to recognize all kind of object, it never sort of thought about, okay, you have to recognize this small pebble. Now we basically try to recognize, this is a human, now this is this is the truck, this is the bicycle, this kind of stuff. Never sort of say, oh, there's a little thing in front that we need to recognize. But of course, later on we have to cover this part and to learn all this stuff. If we can do the same on the fly, you'll be very good. I mean, the same thing in the chatbot situation. Okay, chatbot situation. So you build chatbots, and then somebody say something you don't understand. The chatbot does not understand. What are you going to do? Are you just stuck there, or just say, oh, I don't know? But can you learn? Okay, can you learn by sort of have a dialogue with the person which is talking to you? Talking to you. But that's what we do, right? When human beings, when we say, somebody says something we don't understand, we say, oh, what do you mean by that, right? Oh, do you mean by that? Do you mean this? Or do you mean that? So if the guy basically tells you, it means this, means that, then you learn that, right? Next time you don't have to ask the guy anymore. Okay. So can we accumulate knowledge in this way? So this, if we can do this, that becomes, the system becomes autonomous. Okay. Of course, we still cannot do this yet, and we have some simple examples to show we have some, it's possible to do it to some extent. So again, we're talking about the continued learning, and this case, we're talking about the open world, and we're focusing on post-deployment. We're talking about application, time of application. So in this case, we have this orange lines. Okay, the orange color lines, these are essentially the ones we need to do in order to do this closed world situation. So, sorry, the open world, we need to discover new task, and we also get the ground truth data as well. Okay, ground truth data. And then, of course, some knowledge you can put in the knowledge base. So in order to learn, you have to get your own task, new task. This task not come from the human engineers, okay? And also get your training data yourself. For example, just now you ask the passenger, say, oh, what is this saying? Is this safe? Okay, it's safe. And then the engineer says it's safe, let's go ahead. Then you learn it. So the previous thing, I'm not going to repeat it because it's the bold part that we already talked about before. So the new thing is just basically say we have to identify new tasks and acquire ground truth training data and learn tasks incrementally. So you can see this, we close the loop, right? We don't have any losing part. When model goes to application, then that's it, get into the sink, right? Then it can't do anything anymore. But that's not true now. In the application, we can also discover new tasks and then new training data, and then we close the loop, and then the system will become autonomous. Okay, become autonomous. And so this is essentially the post-training thing. And this is also the same situation for humans, right? We learn a lot of stuff on the job, right? We don't really learn everything from our training or from education, right? When we go to work, and we learn more. Okay, we learn more, but in that case, in that particular situation, we don't really have a book, or we don't have the instructor, but we can talk to each other, right, to learn this thing. Yeah. So we want to put this into the AI agent, AI system. So this is also an example. So see, existing, for example, this is we're talking about the grading bot. How much time do I have? Do I still have?
If you could wrap up in a couple minutes, that would be.
Yeah, I'll try to be quick. Okay, and so this is an interesting example. Okay, interesting example. It says it's a greeting bot in a hotel. And so, for example, in a hotel lobby, you have sort of a chatbots or the mobile chatbots, basically greeting the guest, and have some small talks with the guest. So, for example, the chatbot see this existing guest and, hello, John, how are you today? Right? But what happens if you see the new guest? Okay, and the system has to recognize this guy is new, which essentially is creating a new task to learn, right? This is a new person, I have to learn this person. So that's the creating a new task. Then you want to get some information about this person, right? For example, welcome to our hotel, and then you say differently, what's your name, sir? And so the guy may answer, oh, my name is David. Okay, then you get the class label of this guy, and then you take some pictures, and then you can basically learn to recognize this David. Right? Next time when you see David again, and then you can say, oh, hello, David, how are you today? Right? So basically means you recognize this person, and then you basically can talk to this person just like a friend. And so you can see this becomes completely autonomous. And then I think this is basically the framework, and how do you do this? I think I don't really have a lot of time to talk about this. The first, I'm going to talk a little bit. So this involves quite a few things, okay? When you have a problem, and when you see something unexpected, you have to characterize it. What is it? Okay, what is it, this thing, okay? And you cannot just say, I don't know anything about it. Okay, don't anything about it. And also have to adapt to this thing, and also to learn from this, okay, to learn from this. And of course, you also have to assess the risk. And risk, if you say something, you may say something wrong, right? If, for example, you see a piece of furniture, you're going to say, "What's your number, sir?" Right? That's crazy, and that's terrible. You're saying you're not good enough. Right? At least you know that's a person. Then you can say that. If you see an animal, you see a piece of furniture lying around in the middle of the lobby, you cannot say, hey, "What's your name, sir?" Right? And so this is essentially you need to characterize, and then you need to adapt. And so how do you get your information, the ground truth data? Essentially, you can ask humans, you can ask human to do demonstration, all those can perform some kind of reinforcement learning. And so, okay, I'm going to skip this. This is a pretty complicated. I'm just talking about one final thing. We built a little chatbot system, and this chatbot system essentially says, when I basically I'm doing something for the user, just like Siri and Alexa, and you say, for example, and tell me the weather today, and Alexa will tell you, what's the temperature of those things, and our system is essentially doing that. Essentially, it's a kind of a command, sort of user natural language interface for the user. Okay, and then what happens if the user says something I don't understand? For example, I say switch off the light. The guy does not understand. Maybe the guy only understands the turn off the lights, for example. And then if the chatbot does not understand the switch off the lights, so the chatbot is going to see, oh, switch off. For example, switch off the. Let's have this example. Just give the example of this. So example. So let's say that the chatbot understands switch off the lights, but it does not understand the turn off the lights in the kitchen, or turn off the lights. So for example, the CM system is our system, which basically cannot understand this. So this is like an anomaly detection. You detect a new task. Okay, I don't understand. I detect a new task. This task has to be learned. So next time, if I learn this thing, next time I will have no problem. So how do I characterize this? Because I need to basically acquire some information from you, but I cannot say I don't know anything about this, right? I must sort of say that which part I know, which part I don't know, right? And then I can ask you something specific about this part. I cannot just say, oh, I don't understand this. Can you tell me what is it? And then the guy may tell you something else, and you still don't understand. So, for example, the switch on the lights, switch off the lights, right? But in this case, it's a turn off the lights, so it's a different word. And then you see, oh, okay, so switch off lights is something very similar to what you said, right? Switch off the lights in the kitchen, switch on the lights in the kitchen, and which one do you mean? Okay, which one do you mean? So in this case, the guy may answer, oh, I mean to switch off the lights. Okay, oh, okay, then the system will understand. Turn off the lights means the same thing as the switch on the lights. So next time, then you can say turn off the lights, and then the system will have no problem. Okay, no problem. So this is essentially a continual learning. It's on the fly. Okay, I have some short communication with short sort of dialogue with the human, and then I get this. And next time, I will not have a problem with this particular sentence. Okay. Of course, you need to manage the risk. You don't want to ask people too many questions. People get annoyed, and also, if you don't know anything, if you don't want to give some user some sort of random options, right? You basically make, and you want to be safe. You say, oh, can you say this? Yeah, another way. Okay, so don't get the bad reviews, right? You say, this guy doesn't understand anything, right? And so anyway, so there's a lot of interesting issues involved in order to learn sort of on the fly and to make system autonomous. So let me just close. And essentially, we say in the traditional sort of machine learning, we're talking about the closed world and single task learning, and we don't learn anything in the open world, which basically means a post deployment. Okay, so we want the agent to learn continuously in the open world and on the job, on the fly, after deployment. So to close the loop to make the system autonomous. So you need to discover new tasks and get the ground truth data and continue learning by everything by yourself, by self-initiation and self-motivation. So don't ask engineers to sort of label data, change model, and rerun the algorithm, whatever thing. Okay. However, the current technique is still in the infancy, and it's pretty challenging. It's pretty challenging, and but I think some of those things sort of ready for some applications, at least of simple type of applications. Thank you very much.